Okay, hi. So my name is Varga, and I'm going to talk about brain network simulations. This talk is based on my bachelor thesis that I did under the supervision of Géza Oda. Yesterday I gave a similar presentation for the final exam, and I was supposed to speak about 15 minutes, but I ended up talking for 25. So I hope it will not happen today as well. So we ported our cellular automata spreading simulation from C to CUDA C to see if we could run simulations faster. First, I would like to talk about brain networks, the connectome and criticality, what are these and why it matters. Then explain the mathematical model, which is a cellular automata. We use a cellular automata. And then how we ported CUDA from C to CUDA C, what we learned, what we achieved. And then just briefly, I will show you results of the simulation. And then I will go and talk about the plans, what we plan for the future. And okay, so the networks of neurons comprise the brain. So there are 100 millions of neurons in the brain, in the human brain. And these neurons are connected to each other and they interact with each other. And the structure of the neurons are important for the communication capacity and computational power of the brain. So it makes sense to try to figure out how these neurons are connected to each other. So we want to know how the wiring diagram of the brain, because it might help us understand how it affects behavior, or how a brain malfunction could cause behavior disorders. So we would like to find these wiring diagrams. There are multiple scales on which we can work. So on micro scale we use an MRI, or on nanoscale we would use an electron microscopy. This is so this is an MRI, this is an electron microscopy image. So these are images that someone needs to. So we want to study networks. So there needs to be algorithms to create networks. So graphs, so nodes and edges between the nodes, and this way you can share these networks easier. You can work easier. So there are terms referring to some large-scale data in the area of biomedical research, so genome, proteome, metabolome. So similarly, the term connectome was created. So it basically describes how the neurons, or some larger groups of neurons, are connected to each other, or how the brain is wired together. It's the human brain, the network of the human brain is still largely unknown. The largest precisely explored structural network contains around 300 neurons, which is the roundworms. But the human brain has around around 100 billion neurons, so it's more difficult. The MRI has around a cubic millimeter resolution, so it means that in each vortex, so in each MRI data point, there are 10 to the power of 6 nodes, so 10 to the power of 6 neurons. So the connectome is basically just like a phrase for all neuroscientific investigation between the groups of neurons or collections of neurons. Then I would like to talk about criticality. So it's an experimental result that networks of neurons produce avalanches of activity with power law distribution. So it's on a log-log scale, it's linear. And this might be because the brain operates near a critical point. So what the critical point is the phase between where the activity dies out rapidly, and where the activity is amplified over time. Other simulations suggest that information processing would be optimized at the critical point. For example, correlation length, informational storage, computational power, dynamic range. So there are properties of brain that would be optimal at critical point. However, this hypothesis is still controversial because we are not really sure that what we see is power law distribution, or if it's power law distribution, is it because it's critical, or there could be other explanation for that, other models that explain these power law distributions in data, and also how would the network, the brain tune itself to this criticality, or would it need to be tuned itself? So there are open questions in this area. So the mathematical model that we use is the cellular automata. In the cellular automata model, the simple components together are capable of complex behavior, so that you can imagine a graph where the nodes of the graph are identical, and these nodes are connected to each other through edges, and this is how nodes interact locally, and these nodes have states, and these states can be just a set of possible values, so it's not continuous, and we change so according to these rules, these rules that are identical to all nodes, we change according to these rules, we change the state synchronously in discrete time steps. And the value of a particular node is determined by the previous values of a neighborhood of sites around it. So in the spreading model, we have the activation probability. So let's say that we have an active node. The state could be 0 or 1. The active node has 1, and the inactive node would be, the state would be 0. And if for an active node we set it to inactive with new probability, or and we set an inactive node in the next time step to active if so we calculate the weighted sum of its active neighbors, and if this value is above the threshold, then we set it to active with lambda probability. And we can also create inhibitory edges, so where the weight would be negative, or undirected edges where we don't connect to, so if there is a connection between two nodes, then we just add it in one direction and not in both directions. So the very high level overview of the program would be, I will be using pseudocode that is similar to Python, but we were in C, but I think it's easier to read and understand. So we basically read the file, and then we transform this data structure into a format that is easier to work with. Then we run the simulations for all parameters. Then we just write the relevant results to file, and after that we take a look at it. So this is more detailed. So this is one discrete time step. Again, so we go for all nodes. This could be parallel. So this is what we made parallel for all nodes. So we put one node in one thread, and then we would check if this node is active. If it is, then we deactivate it as it is here. Or if it's not active, we calculate the weighted sum of its active neighbors, and if it's over a thread. So if the weighted active neighbor count is over a threshold, then we activate it in the next step with lambda probability. So the benchmark results, so it's 12 times faster than the original code. It's good, but it's not great. So it's good because the simulations that took 2 weeks are done in almost a day, but there could be so it's good, but not great. So it was easy to calculate. So it was easy to port from C to CUDA because one thread, so calculations in one thread are independent of other threads, so there is we don't need to synchronize, so why we couldn't achieve more is probably because the network is large, so we have almost 1 million nodes and many edges between them, and it's large, and this is why, and inhomogeneous. So this is why we needed to store the network and the state of the nodes in global memory. I couldn't find a better way, and also because it's not homogeneous, we needed to. So when we calculate the sum of neighbors, so for example, so here we go through the neighbors, and it's the degree of nodes vary, and this is why some threads may be waiting for others where the node has a high degree, so it has many neighbors. So this is why some threads might be idle. And so this is the result. This is a result that we got. So PT is the survival probability. So the probability of the network. So at the beginning of a simulation, we set a node to active, and we see how this evolves. And the survival probability is the probability of the network having at least one active node at t time step. So you can see it's declining, and lambda is the activation probability. We changed it from 0.5 to 0.555. So the activation probability is higher the longer it survives. And we also used the 30% of the node. So the 30% of the nodes were inhibitory. This means that these have a negative weight. And we see that it's here, and it's close to power law distribution. We could plot this. So it's basically we try to fit a linear here. So this delta effective is, it shows that the steepness, so the derivative doesn't change that much here. And yeah, so this is just one example. I didn't want to talk too much about that. So I'm thinking about a better algorithm, because so far we only ported C code directly to CUDA, and so maybe we could just use another algorithm. And I think we could, because the only nodes that could change their state are the active nodes and their neighbors. And we could maybe keep track of these nodes and calculate new states only for these nodes, and it would be probably a big improvement. But I don't know, because I didn't write the code yet. So here we would have an active node. We would need to take its neighbors. We would have to keep a list of its neighbors, and we would only need to check in each discrete time step whether the states of these nodes change or not. So let's say this changes, then we would need to add these nodes to the list of nodes that we watch. And then if it deactivates, then we would need to remove these nodes, and that would be the other algorithm that I'm planning to do. So this complicates the program, and we need to implement all supporting data structures and the algorithm itself. But I think it could improve significantly for cases where the active node count is low, and maybe we could even switch between the algorithms depending on active node count. And in this case, because we don't need that much parallelization, maybe a CPU would perform better. So I think it's really interesting. It will be really interesting to see how this algorithm affects the performance. So the other thing that we should do in the future is running simulations on more networks. So the underlying network. So we only run the simulations for now only on one network, and we could, this Open Connectum project, we could download from this project, we could automate downloading more network data files, transform them, and then run simulations automatically on these data sets. And we could analyze results, look for patterns in the network, in the graphs, find connection between these properties of the network and simulation results. And yeah, I think it's really interesting. And let me know if you would like to try this program for your spreading simulations. I don't know if any of you are working with cellular automatas, but if you do, just let me know and we could see if you could use this program. And I think, yeah, that's it. If you have any advice for us, how we should continue in the future, just let me know now or when we drink the coffee. And if you have any questions, just let me know and go for it.
I have a quick question, then I'll jump to the second line. So, how many connections do you have roughly? Order of magnitude, 10, 100, 1,000?
Oh, it changes. So
yeah, but roughly, order of magnitude, 10, 100,
10 to the 7.
Per node.
Per node is
10.
around
10. So per node about 10 connections, all right?
No. The average connection number is about 500, but it's very homogeneous.
Oh, fine. So about 100, okay. The other question is, so you should look into your random number generator. You should profile this code, am I right? So I just estimated, so you have 10 to the 6 nodes. Each step you need to generate 10 to the 6 random numbers. You do 10 to the 6 steps. It's 10 to the 12 random numbers. That's kind of high to do already in itself. You're very patient. You run already for 2 weeks. I never would ever consider without checking into where I spend most of my time running for 2 weeks. So you might find actually that you wasted it somewhere else. So you definitely should profile it. I suspect the random numbers could already be a good step to speed up. If you really run 10 to the 12 random numbers, as I estimated.
Okay, I couldn't really follow your numbers, but
you have a million time steps, a million nodes, and each step, in each node, you need to run a random number, roughly. Either because you want to flip it up or you want to flip it down. It requires more or less. Okay, it depends on what your k value is. But that's the order. So I suspect you already waste quite some time.
Okay.
Numbers. I would profile this code before you do anything else.
Okay, so let's continue this in the cafe break and let's dive in a second.